In this example, we're given that tangent theta equals 2/3 and sine theta is less than 0. We want to determine sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So we'll be using the double angle identities we see here below, but we first need to determine sine theta and cosine theta from the given information. Tangent theta is equal to 2/3, which means the terminal side of theta must either be in the first quadrant where both the x and the y coordinates are positive, or the third quadrant where both x and y are negative. Remember, a negative divided by a negative is still positive. The reason they're telling us that sine theta is less than 0 is because if sine theta is less than 0, then y is less than 0, meaning y is negative. And if y is negative, then x also has to be negative in order for the tangent function value to be positive. So the terminal side of our angle theta is going to be in the third quadrant. So let's go ahead and sketch a reference triangle in the third quadrant. Doesn't need to be to scale. This would be our reference angle. And since tangent theta is equal to positive 2/3, the opposite side could be labeled -2, and the adjacent side would be labeled -3, resulting in a positive tangent function value. Now we need to determine the length of the hypotenuse using the Pythagorean theorem. So let's go ahead and call this r. We're going to have r squared is equal to -2 squared plus -3 squared. So we have r squared equals, this will be 4 plus 9, so that's 13. Now we can take the square root of both sides. So r is equal to the square root of 13. Remember, r is always positive. So now we can replace r with square root 13. And we needed this information to determine sine theta and cosine theta. So sine theta is equal to -2 over square root 13, and cosine theta is going to be equal to -3 divided by square root 13. We're not going to rationalize these unless we have to when applying the double angle identities. So for sine 2 theta, we'll be applying this identity here. So sine 2 theta is going to be equal to 2 times sine theta times cosine theta. So we'll have -2 divided by square root 13 times -3 divided by square root 13. Let's put this 2 over 1. Nothing here simplifies. We'll multiply across the numerator and across the denominator. Here's the reason why we didn't have to rationalize. Square root 13 times square root 13 is just 13. And the numerator we have 2 times -2 times -3. That's going to be 12/13 for sine 2 theta. Now for cosine 2 theta, we have a choice of identities. Let's just go ahead and use this one here that involves cosine theta. So cosine 2 theta is equal to 2 times cosine theta squared. So we'll have -3 over square root 13 squared minus 1. Let's go ahead and put this over 1. Let's go ahead and start by squaring this. We're going to have 9 over 13. So 9 over 13 times 2 over 1 is going to be 18/13 minus 1, which is 13/13. So we have a common denominator of 13, and 18 minus 13 is equal to 5. So cosine 2 theta is equal to 5/13. Using the reciprocal identity, tangent theta is equal to sine theta divided by cosine theta. Tangent 2 theta would be equal to sine 2 theta divided by cosine 2 theta. So we could apply this identity here, but we can also use the quotient identity to simplify our work. This would just be 12/13 divided by 5/13, which is the same as 12/13 times the reciprocal, which is 13/5. The 13s simplify out, and we're left with 12/5 for tangent 2 theta. Now I'll go ahead and apply this double angle identity anyway, but you can see this is pretty straightforward if we already have sine 2 theta and cosine 2 theta. But using the identity, we would have tangent 2 theta is equal to 2 times tangent theta, or 2 over 1 times 2/3, divided by 1 minus tangent squared theta, which is 2/3 squared. So we'd have 4/3. This is going to be 1 minus 4/9, which will be 5/9. Writing this as a multiplication problem, we'll have 4/3 times 9/5 This simplifies, and of course the result is the same. This is 12/5 for tangent 2 theta. So regardless to which method we use, the result is the same. I hope this was helpful.